Alright, students. So in this lecture we're going to be talking about the arc length of a function. So let's say you have a function and just so happens to be in the first quadrant here. We'll say this is just f of x, just some sort of generic function. And we want to find what is the arc length along that function between an x value of a and the x value of b. So kind of have that outlined there in blue purple. So one way that we could approximate this using a pre-calculus method would be to place maybe locate a point somewhere along that curve. We'll call it x1, y1. We'll call that original point x naught, y naught, or x sub 0, y sub 0. And then just continue that process. Pick several more points along the curve, and then using pre-calculus, just use the distance formula to approximate the distance between those points, and then just add all of those up. So the distance formula, if you remember, is the square root of x2 minus x1 squared plus y2 minus y1 squared. So each one of those distances, we call this like d0, d1, d2, d3, d4, and so on and so forth, however many segments we had. Something that could be helpful for us would be if we were, rather than worried about the x2 minus x1, y2 minus y1, is just to say, all right, this vertical distance between those two is, we're going to call that delta y naught. The horizontal distance between those 2 points would be delta x naught. And we could say, all right, well, the distance there for that first segment is that delta x naught squared plus delta y naught squared, and then take the square root of that. Of course, distance formula, if you remember, is just based on Pythagorean theorem, and it's really easy to see in that formulation right there. So then obviously you would have this is delta x1, delta y1, delta x2, delta y2. So for each one of these little segments you'd have a delta, and so therefore this s is going to represent the distance of that, or the length of that arc right there, would be the summation of all of those distances. So for instance, right up here is d naught. So it would be the summation from I equals 1, I probably should have put from I equals 0. But anyway, from I equals 0 to n, or I equals 1 n of d sub I. So d1, or d0 plus d1 plus d2 plus d3, and so on and so forth, however many segments we had. So I'm just going to keep that 1 right there. So we've got the summation and then the square root, just plugging that formula in, delta x sub I squared plus delta y sub I squared. All right. We're going to do a little bit of manipulation of this. So the first thing, this is what we call in mathematics an unmotivated step. So you might not think of this on your own, but fortunately someone somewhere very smart with an end in mind thought of this step right here. And that is, we're going to take the second term and both multiply it and divide it by the same thing. So that is multiply and divide it by delta x sub I squared. So we're multiplying here and dividing it there. And of course, if you remember, if you multiply and divide something by the same quantity, then that original amount stays the same. It'll just look different. Basically, we're multiplying it by 1. So I'm going to do a little bit of a manipulation here. So keeping that summation the same, the square root. What we can do now is we can factor out a delta x sub I squared out of each one of those terms. All right, so if we look back here at that previous step, we had a delta x sub I squared in the first term and a delta x sub I squared in the second term. We can factor that out. The first term, all it's left with is a 1. And in the second term, we're left with this very curious delta y I over delta x, and I'm going to just group that together and put the square on top. We'll zoom in here a second. So zooming in here, if you remember, the property of square roots is that if you have the square root of two things multiplied together, you can actually split them up and say the square root of the first thing times the square root of the second thing. And the square root of delta x sub I squared is just going to be delta x sub I. So that it reduces nicely. And then we have, obviously left over here, square root of 1 plus that quantity. All right, and then we get to the calculus step where we say, all right, we don't want n number of segments. We want to increase the number of segments to infinity. What happens as those segments get closer and closer and closer, and their number becomes infinite? So we apply the limit process, or we take the limit rather of this summation. So the limit as n approaches infinity of the summation of all of those segments. I'm going to just rearrange these two terms here for representation purposes, which we'll see here in a second. And we know that the limit of a sum is the integral, the antiderivative, the definite integral specifically. And it's going to be from a to b. Those are our x values. And then when we take that limit process, those deltas become differentials, so dy over dx squared. And the same thing, that's why I put this delta right here, because that just becomes dx. And that's our formula right there. That is the calculus formula for arc length. Sometimes you'll see it written like this, where rather than dy over dx squared, you've got f prime squared. That's fine, it's essentially the same thing. So you say, all right, great, that looks helpful. I'm not sure I believe it. And I say, okay, well, I didn't believe it either. Let's go ahead and apply this with maybe a linear function, something that we can easily use pre-calculus to determine the length, and see if this will work as well. So here is a very straightforward function, f of x equals 2x plus 3. Sorry, it's not very accurate here, but we do have a y-intercept of 3. At an x value of 10, we are at a y value of 23. So we've got 2 points here, 0, 3, and 10, 23. And let's say we want to figure out what is the length of this curve. Curve happens to actually be a straight line between those 2 points. And we can solve that using pre-calculus methods, namely just with the distance formula. So that would be the square root of the sum of the squares of the differences. So that's 10 minus 0 and 23 minus 3, so that turns out to be square root of 500, which is 10 root 5. That's the pre-calculus way. Now, if this new formula that we just derived is valid for functions, then it's valid for any functions, quadratics, cubics, trigonometric functions, but also linear functions. So we can apply that here. So this is s, we mean arc length, is the integral from 0 to 10. Those are my x values. 1 plus, and then this is going to be the derivative of the function. So the derivative of 2x plus 3 is 2. So you can see 2 squared there. Squared because that's from the formula. And then just simplifying that, square root of 5. The antiderivative of that, sorry about this, I forgot to put the x right there. It should be an x. It would be square root of 5x. So then that's evaluated from x equals 0 to x equals 10. So plug in 10 for x, and we have 10 root 5 minus 0 root 5. Final answer 10 root 5, which we can see matches exactly what we had over here originally, 10 root 5. Okay, let's do one more example, maybe two, I don't know, we'll see what we have in store. So here we have part of a function. We'll say this is the region of y equals x cubed over 6 plus 1 over 2x. And we want to find what is the length of that curve between x equals 1/2 and x equals 2. So that region right there. Sorry, my graph is a little bit disproportional, but you get the idea. I mean, I'm not even showing the whole cubic, just this region right here. So first little thing that we do is to find the derivative. I found that sort of helpful. So obviously, derivative x cubed over 6 is 3x squared over 6 plus, if you want to think about how to rewrite that, in case you forgot for the derivatives, write that as 1/2 x to the negative 1. So the derivative would be negative 1/2 x to the negative 2. We can simplify this. 3 over 6 to 1/2. X squared stays the same, the minus, and that x to the negative 2 goes down in their denominator. Now we are fully equipped to write the formula, so that's going to be the integral from 1/2 up to 2 of the square root 1 plus, and then we'll just go ahead and write the derivative squared dx. Ta-da! Then at this point you're welcome to use whatever methods you want. I'll just use the calculator, and we end up with 33 over 16. Declare ourselves finished on that one. Now, here's a note. Some of the homework problems that you face may have x as a function of y rather than y as a function of x. And that's the case. Everything's going to be just in terms of y values. So obviously you're going to have your lower y value to your upper y value. Instead of having dy over dx, it's going to be dx over dy squared, and then our variable of integration is going to be dy rather than dx. And so very quickly we'll do a problem that will involve that. So everything seems to be in the first quadrant today. Let's say we have a graph. This is just a region of this equation right here. Y minus 1 quantity cubed equals x squared. We're interested in this on the x region from 0 to 8. If we solve this function for x, we get x equals plus or minus the square root of y minus 3. Now since we're interested in this region, positive region, x values, we're going to just use that positive side of the equation. So that being said, I can take the derivative because I know I'm going to have to use that here in a second. So that's going to be 3 halves times y minus 1 to the 1 half. That's if you pop down the 3 halves, then power it down, subtracting 1. And then applying the chain rule, derivative of the inside is just going to be 1. And then, I really apologize, I know this is a little frustrating. So here we've got value of 1 all the way up to 8. So 1 on the y-axis, that's 0 on the x-axis, and then 8 and 5. Sorry, that 8 is really hard to see. So when we plug this into the formula, our lower bound is on the y value, or on the y-axis rather, so that's going to be 1, and our upper bound is 5, so we're working our way up this way. So 1 plus 3 halves, y minus 1 to the 1 half, all squared, dy. You can plug that into the calculator, and you end up with a nice answer, 9.073. Alright, so in this video we talked about how to find arc length, did the derivation, did a few problems, both y is a function of x and x is a function of y. Thanks for watching.